Good afternoon, everybody. Today I'd like to talk about the transformation of geometry contained in building information models into a format appropriate for whole building energy simulation. This is a key issue for me. I've been working in this area for about 12 years now, and the major bottleneck is the fact that contemporary business practices regenerate the information that has been contained in the BIM, but it regenerated in another tool, and we know about the inefficiencies, error-prone nature, and basically the waste of time and money that these processes can result in. So today I'm just going to chat a little bit about the technical issues that accompany this kind of problem. I'm going to describe the conceptual solution, then we'll look at the process, the detailed process for this solution, then we'll look at how this process has been applied to the NASA Ames sustainability base. Okay. So, when an architect creates a building information model, it should contain most of the information required for detailed building energy performance simulation. There are certain omissions, and I think I'll cover those over the course of the presentation. But, however, when we look at the different architectures of the BIM model and of the energy simulation model, there's a marked difference. We see here that the BIM is detailed, and we have a simplified representation for the energy model. The simplified representation is due to a historic architecture of the geometry that basically relies on one-dimensional heat transfer models within the energy simulation program. And what that means is that heat transfer is performed orthogonally to zone boundaries. And the end result is that we end up with a series of interconnected shoeboxes, as can be seen here. And first and foremost, this results in what's called, or has been termed, a thin wall model. And that is that the wall representations have no thickness. Thickness is only entered as a property. And we see here there are many gaps visually evident in this model. We also see here that there's a gap between the exterior facades and the shading. And that's essentially all I'd like to say. So walls are represented as planes, and heat transfer is perpendicular to the zone boundary. And this is important to take with us as we move on. So with this in mind, zone boundary or space boundary, it's the same thing in this context. The required space boundaries for energy simulation are not exported by the current day CAD tools to the IFC data format. So all of this work is based on the IFC open data format. So space boundaries are, in essence, we have a single boundary that surrounds this room, but when we break it down into detail, we require second-level space boundaries that represent the heat transfer surfaces. So that's an individual space boundary per wall, window, door, floor, ceiling, column, etc. But in the interest of enclosure, and again these simplified heat transfer models, we also see here the third-level space boundaries. These are cases where there is actually no heat transfer available, or sorry, not available is the wrong word to use, possible in the context of the simulation engine, and these are must be included in the energy simulation model for zone enclosure, and these are represented as adiabatic surfaces. So what we propose in this particular project is it's an overall concept that relies on a tool that will generate the required level of space boundaries. So the LBNL semi-automated process has two major components. The first being geometry, and this is the focus of today's talk. And the idea is that we will remove the need for the error-prone, subjective, and time-consuming and waste of money processes that regenerate building geometry that's already been defined by the architect. And this is what the Space Boundary tool is essentially going to help us out with. The second component is synergy. And this looks at the definition of MEP systems for the purposes of whole building energy simulation. Currently, MEP definitions within BIM are not transferable or reusable in energy simulation, and the Synergy project has been ongoing in the US since 2009. I worked on it myself for 3 years, and this hopes to rectify that issue. It's currently in prototype mode as a Space Boundary tool, and Synergy is available as a free download, and Space Boundary tool should be available as a free download as well in the coming months. It was available previously and for some reason it's been taken down. I'm not sure why. Synergy is about to have a major cash injection, I believe, and over a 5-year cycle. Okay, so the process in detail. There are two issues here. First and foremost, we need some manual data input, and there are some workarounds required, primarily in the area of a linked material library that will be referenced by Space Boundary Tool in step 7 here. Okay, so the process from a high-level overview is we input our data to our BIM authoring tool, and I must say here that we just used ArchiCAD and Solibri and Energy Plus as they're the tools we're most familiar with. We're not particularly aligned with any particular vendor or anything like that. The process also works with Revit-based export, and we're open to other suggestions from other CAD tool vendors. So the building is modelled in ArchiCAD, exported to the IFC file format, and is checked for errors in the Solibri model checking tool. And this is a repeatable process until the model is of sufficient quality. The IFC file is then imported by Space Boundary Tool and mapped and linked with the materials library to generate the geometry required by the energy simulation model. Okay. So just to put things in context, the NASA Ames sustainability base is a very difficult, and it was an unusual choice for a prototype project. It's a very difficult building for one reason, that the facades are essentially concentric circle segments with a center point a couple of 100 feet away from the, I guess, the topmost facade here. And what that resulted in was a series of non-orthogonal interior wall intersections that had a number of different problems. So I talked to different people yesterday about tolerances, and 20 mil or 10 mil seemed to be an acceptable tolerance within the industry, but unfortunately we have a 0 mil tolerance for this process, and that's one of the limitations, and I'll talk about that at the end. So we have a number of issues that arise due to the modelling capabilities of this particular tool and of the CAD tools in general. We see here the concentric circle segments have been simplified to linear sections on the facade, and therefore prefabricated construction purposes, and it ends up resulting in little slivers that are not contained or not defined within the model. So these are tiny sections, but due to the nature of the heat transfer required by the energy simulation tools, it generates a number of errors for our post-processing. So just to be aware of errors like this, and again the high tolerance requirement of a Space Boundary Tool. So the first step I mentioned, just inputs and general information. The building was in Palo Alto, so we just took the San Francisco city location, realized it wasn't appropriate, and we changed the coordinates to Palo Alto. We also inputted the site elevation and the surrounding site conditions, such as trees and neighbouring buildings, etc. Okay, I talked about the mapping library that was required. So we needed to develop a workaround because the properties that are needed for energy simulation are not currently exported to IFC from the different CAD tools, although they can be defined within the CAD tools themselves, just a short limitation. So any given, say, wall cross-section or floor cross-section is made up of a number of material layers, and these material layers are mapped individually and combined at runtime. So that's just based on a string match with our external library. So we use a kind of a proxy workaround in that case. It's a more simplified approach then for windows and doors, and it's a string match per construction type. And it essentially aligns the different wall, window, door instances, etc., with the appropriate material and thermal properties. Okay, so as I mentioned there, we also account for zones and shading. It's just an example of the floor plan layout. Large open office spaces are clearly evident in kind of a light purple colour. And to generate our final BIM, and that's just an example representation of the final BIM in ArchiCAD prior to export to IFC. So the export to IFC takes on two important considerations. The first of which is that the area volume calculation must be preserved. Energy Plus likes to work in shoeboxes and at times can mistakenly calculate the volume of a given zone. But you can override that, and what we intend to do is to override it for every instance. So we rely on the accuracy of our tool to accurately calculate the area and volume of each zone. Furthermore, we don't want to export any space boundaries. because our space boundary tool will generate the first, second, third level, fourth level and fifth level as needed, whereas the BIM authoring tool here will only export first level, I believe. Okay, so we export then to Solibri Model Checker, which is, I think most of the audience here are familiar with the model checking environment, but we developed a customized rule set for this approach. So this is based on, again, those tolerances that I talked about earlier. We also ensure that, for example, walls must touch ceilings, walls must connect with the slabs, and that the zone boundary is flush with the wall, etc. So typically, when I first received the NASA Ames BIM, I had over 700 different errors, and it was interesting to note that I had to actually send the BIM back to the contractor and say this isn't acceptable, and I gave a number of different modelling guidelines, and we formalised those guidelines in a paper that we published this year, and that will be available as a link at the end of the presentation. But it's very important that the BIM is drawn a certain way for energy simulation, and that became pretty evident with a model of this size. Okay, so then SBT itself, it adds the space boundaries to the BIM through what's a graph theory-based approach to identify zones, the heat transfer element, and the corresponding other side zone or exterior environment. So it passes through Space Boundary Tool, which is the secret sauce in this whole process, to generate a space boundary representation, which is viewed here in the FCK viewer from Karlsruhe. So we had a number of different test cases that we had to manually check and so on to make sure our space boundary tool was working in accordance with our expectations. The space boundary tool itself it's a semi-automated process, so there are some rudimentary inputs that are required, for example, number of time steps per hour. I don't know how clear it is here. You can click the terrain for your building. You can talk about the different types of shading and shading algorithms you'd like to use within the package. They all have a different effect on the accuracy and the runtime of the particular model. Okay, and what we end up with then is the energy simulation representation of the building itself. And we can see here that's in line with an earlier image I showed, but we can notice the heat transfer surfaces on the roof in particular. And when you compare this to a previous image I showed, we had to remove the skylight domes due to the complexity associated with the zoning and the daylighting consequences of that, and we had to develop a workaround there. Okay. So finally, the validation process, we also needed to check using a wireframe model how our Energy Plus import actually looked in real time, after the transformation process. So this here's an example of the building in wireframe mode with the different color representations for different element types. Okay, so to conclude, this process delivers significant efficiency improvements, and to date, a lot of the energy modeling activity, because it took so long, and Bazianets in one of his earlier papers claimed that 90% of the modeling effort was associated with the building geometry, and for that reason you could only develop one real model in detail, and if the design evolved past that point, then your model was out of sync with your design state. So I think this process enables a synchronization of the design with the energy model predictions for that particular design. Okay, and I think it's also important to note that we're coming into an age where we're looking for life cycle predictions, and from an energy perspective, it's imperative that this model is then carried through to operation, and it reflects all of the changes that occur. And I believe that this is essential if we're to bridge the performance gap between these predictive models and what's actually happening in practice, and that gap can be quite substantial in certain cases. Okay, I mentioned earlier that there was a zero tolerance at the moment, and that was one of our key limitations for this project. And there's talk and a proposal put together to the United States Department of Energy for a tolerance adjustment tool. So that should be funded once the, I guess, ongoing budgetary issues are resolved over there. I won't say any more on that. Furthermore, we've also talked about the kind of shoebox type models and orthogonal heat transfer, and we also need to update this particular prototype to account for curved surfaces. There is actually, in the latest version of SPT, they have a workaround for curved surfaces, so that actually that works as well. Okay, so the future work. I think a lot of this audience are familiar with the model view definitions. I just included 3 example definitions here. I think I've say the architect, structural engineer, and heat transfer specialist or energy modeling expert, respectively. But in order for BIM to contain the properties and property sets that are appropriate for energy modeling, this requires quite a large scale project and initiative. So to that effect, I have joined up with the International Energy Agency Annex 60, and this annex aims to enable the exchange of this particular information through the IFC data format. So that's a 5-year project, and the technical activities will kick off next month. So, I mean, it may be surprising to note that, say, of the currently available and most popular tools such as Energy Plus, IES, Transys, Modelica, etc., they all have very different representations of the same information. They use very different property sets, and it's very, very difficult to align these particular definitions. So it should be a very interesting and challenging project, and I have a lot of experience on that based on a data model, an interoperable data model that I created called Sim Model, in conjunction with Richard C. from Digital Alchemy Pro, for the purpose of interoperable data exchange of building performance simulation data. So that'll be the starting point for the IE Annex 60 activities. So finally, I'll just leave with the 2 resources. So this has been a published technical report at the Lawrence Berkeley National Lab, and the model authoring guidelines are also available from the IBPSA conference that was held last August. So with that, I'll conclude. Thank you.
Take a seat, James.
Sure.
Any questions for James? I think I found that really fascinating, actually. I think what I'd like to know is why design a building with concentrically circled facades? It's just interesting to reflect, isn't it, that it's only since we've really started using this technology properly that we have suddenly all these wonderfully shaped buildings appearing, which is great, you know, but somebody's still got to make them and build them, haven't they? Any questions?